Okay, I want to show you how to build a model for colliding pool balls. I'm going to go over the physics fairly quickly so we can focus on the Python stuff. And there are more than one way to do this, but this is the way that's fun, okay? The fun way to do it. So, I mean, you can imagine how complicated it can be to model balls that collide because if it doesn't hit straight on, then it's hard to know what angles these two things go at. Yes. If I assume it's an elastic collision, then the we'll call this ball A and ball B, and this is 1 beforehand, this is 2 afterwards, then KA1 plus KAB1 equals KA2 plus KB2. And this is the kinetic energy before is equal to kinetic energy afterwards. That's true for an elastic collision. What's also true is the momentum before is equal to momentum afterwards. PA1 plus PB1 equals PA2 plus PB2. Okay, but we don't want to, if you do it this way, and I know the initial velocity here, and I know this one's, let's say it's at rest, but it doesn't really matter. At the end, I have too many velocities to really make this an easy problem. It's doable, but it's very difficult. So we're going to do it a different way. And that is to say that the pool balls are springs. Okay, so imagine that I have two pool balls colliding. So I'll draw a little bit bigger, pool ball A and pool ball B. That's a terrible ball, look at that. Okay, and so if they overlap, because they're not real things anyway in Python, if they overlap, I'm going to have a force pushing these apart in the direction of this overlap. And the magnitude of that force will be proportional to this overlap distance. So I'm going to model the balls as springs. And if I do that, I can use the momentum principle, which says that F net on A is equal to the change in momentum of A. F net B equals the change in momentum of B. And these are vectors. And if I calculate the force on A, the force on B is just going to be the exact opposite because forces come in pairs. So here's what we're going to do. Number one, I'm going to find the motion of the balls using the definition of average velocity. So if I break this into small time slots, time intervals, then during each interval I can update the position of the ball with this. RA1 vector equals I'm just so excited about the spring thing. Plus PA over M delta T. This is just a definition of average velocity, but this says that if I know the position and the momentum, I can find the new position. And then I can do the same thing with the momentum from this. I can say PA2, gosh, I'm having a problem here, PA1 plus FA delta T. So I'm going to calculate the force if there is one due to the overlap. I'm going to use that to update the momentum. I'm going to use that to update the position. And then I'm going to do that for the other ball too. And then I just keep redoing that every time, but I need to recalculate the force if they are overlapping. So that's the main thing. If they're overlapping, then I'm going to say the force on this is going to be, let's call this FA. First, I'm going to calculate this vector here. I'll call it RAB. It's from A to B. It's from the center to center. And if that RAB, the magnitude of that, is less than this distance, which is twice the 2R, then there'd be an overlap and there should be a force. And then I can calculate that force, FA, as negative K times 2R, that's the radius of each ball, minus the magnitude, I'll write it this, RAB, right? So that's a scalar, that's a scalar. Now I want to make this a vector, so I need to multiply this by RAB hat, the unit vector in the direction of RAB. And that will be the force on A. And then the force on B would just be the opposite of that. Okay, so I'm going to use these masses, and that's the radius of the ball. Let's just go ahead and make some balls and collide them and check to see it all works. And then I want to show you two successive collisions because that's really what I want to work on. And let's jump over here to Python. So I'm using GlowScript VPython, or it's now called Web VPython. And this is Python, but it's running in a web page. And I will give you the code down below so that you can have it and you can play with it and change things and make it your own. And that's what really is the best part, is when you play with the code. You can't break it, right? Because if something goes bad, just reset the code. If you want to copy it into your own program, that's fine, but you can always go back to the way it was. Okay, so I have the mass of the ball and the radius of the ball. The first thing I'm going to do is to make the two balls. So I'm going to make a cue ball and the one ball. I think the one ball is yellow. So let's put the one ball at the origin, put the cue ball off to the side. So I'll say, let's just call it, I'm trying to think what should I call it. What did I call it before? I'm going to call it BC for the cue ball. The ball cue. I don't know, that's a dumb name. But it's a sphere. Its position is going to be equal to -0.200. So it's 0.2 meters to the left. It has a radius. So this is one of the nice things about VPython. If you haven't seen it before, we have these built-in objects like a sphere, and I'm going to show you what it looks like. It actually makes a sphere, and I think that's awesome. I am going to do something over here too. Make trail equals true. And so the different parameters for the sphere, you can find it on the GlowScript help site. But if I run that, this is super awesome. I get a sphere right there, and it's at the right location, the right distance. And this is actually a 3D environment. I can rotate it around, and I can zoom in and out and stuff like that. So it's a 3D environment, and that's pretty cool. Now let's make let's give this object some properties. So I'm going to say bc.m. I'm going to give the mass property of the object. I'm going to set it to mball equals. Now I want to set the initial momentum too, and let's see. I just need to pick a value here. So let's just say bc.p, the momentum, is going to be bc.m times the vector. I'm going to say, let's just say 100. So it's got 1 meter per second going that way, and that's fine. Let's just go ahead and model the motion of the single ball just so you can see how that works. So I'll say while t is less than 2 seconds, I'll run it for 2 seconds. I do need t equals 0. I need a time step. I'm going to put this at 0, 0, 1, because when they overlap, and in fact, the overlap doesn't matter. Momentum is going to be conserved no matter what, as long as the two forces on the two balls are the same. So it should be fine. So the first thing I'm going to do here is rate 1,000. So this says don't do more than 1,000 calculations per second. And if I do that, then this will run in real time, right? Because if each step is 1/1000th of a second, it's going to run in real time. So you can change that if you want to run it fast, or if you want to run it slow, you change that rate statement. So now what I'm going to do is I'm going to, let's just do this. Let's call this FC. This is the force on the cue ball is going to be equal to vector 0, 0, 0. There's no force. So I'm going to first update the momentum. I know that's dumb, but it'll be fine. So I'm going to say bc.p equals bc.p plus fc times dt. Okay, so that didn't change. Now, one thing, if you haven't done this before, you may notice that it looks like the bc.p's would cancel, but this is a make equal to sign. This is not an algebraic equal sign. So it takes the old value of the momentum and sets it to the new value. Now I'm going to update the position. bc.pos is the vector position of the ball. So it's just I'm going to update that. It's going to be plus bc.p times dt divided by the mass. And finally, I want to update time, or it'll run forever, and that should be it. So let's just see what happens, see if this actually runs. I mean, that's boring, but it worked. Okay, so now let's put the cue ball, the one ball in there. So B1 is the one ball. It's going to be a sphere. Its position is going to be at the origin. Its radius is R. Its color is yellow. And then make trail equals true. Trail equals true. Okay, and then it needs a mass. B1.m equals mball, not blah. B1.p, this one's going to be at rest. So it's going to be, I could put B1.m times vector 0, 0, 0, but if it's multiplied by 0, it doesn't matter. And then down here, okay, now we can start doing some cool stuff. Let's just run this and see. Let's just see if it's there. There's my ball. And it passed through because this is just a calculation. If I didn't tell it to do anything, it's not going to do anything. Okay. So the first thing I want to do is to find out the value of this force. So to do that, I'm going to calculate RCB, C1. This is the vector from the cue ball to the one ball. So I'm going to say B1.pos minus BC.pos. So that's my vector. Now I can say if the magnitude of RC1 is less than 2 times R, then they overlap. And I'll need to set the force as something. Now, actually what I want to do up here is to say FC equals vector 0, 0, 0 at the beginning of the loop. Because every time I want to check and see if that force is indeed 0, I mean, or if they're overlapping or not. If it's not, I'm going to leave it at 0. Okay, so I don't need this one up here. It doesn't really matter. Just going to leave it because I don't really care. So now I can calculate the force FC equals negative K. Oops, I don't have K. I'm going to use K equals 500 newtons per meter. And you can change that, and you should change that and try seeing what happens when you do that. Times 2 times R minus mag RC1 times norm RC1. So norm is a built-in function into Web VPython. I want to say GlowScript. It used to be called GlowScript. That returns a unit vector of a vector, and then mag returns the magnitude of a vector. So those are just built-in functions that make things easy. Now let's just think, if they're overlapping, then mag RC1 is going to be less than 2 times RC, so that's going to be a positive number. And then I'm going to have it in the direction of RC1, but I want it to push backwards. So that's why that negative sign is there. I think that should be there. So that should be good right there. That's BP, BC. Now, I need to do the same thing for the B1.P equals B1.P minus FC times GT, right? Because it's the opposite force. I don't need to recalculate another force. It's the same force, just in the opposite direction. Now I need to update the momentum of the position of 1, B1.pos equals B1.pos plus B1.p times dt divided by B1.m. And I think that will work. Okay, so let's see what happens if I run this. It worked. Okay, now if you have two equal object things and you have a direct head-on collision, the only way to conserve momentum and kinetic energy is for the original one to stop and the other one to continue at the same velocity. And that is what happened. I don't need to run this for 2 seconds. That's even too long. Let's just do 0.5, 0.6. It doesn't really matter. Okay, so there you go. Now, let's do something awesome. What if it's a glancing blow? If I move the cue ball up a little bit, when they collide, that force pushing them apart is going to be at an angle, so the momentum will change in the y direction for both of them. So let's move the B cue ball. Let's give it a y value. Let's say, what's the radius? Is 0.05, so let's say 0.02. I'm just picking a number. That's all I'll do is change the initial position. And let's see what happens. Okay, so, I mean, it looks good, but how do you know if something's good or bad? Well, I can check the kinetic energy, and I can check the momentum. I'm just going to check the momentum. You can check the kinetic energy on your own as a homework assignment. So let's just print the momentum before and the momentum afterwards. So before the loop, I'm going to say print P total equals, and it's just going to be equal to B1.P plus BC.P. And I guess I should put units. Kilogram meters per second. Now down here, once it's done, I'm going to do it again. I'm going to say print. I can just put the whole thing. Let's copy it. Probably could have typed it already though. Okay, so let's run it. Same thing. Okay. And you'll notice the total momentum in the y direction started off as 0, afterwards 0 too. And you can change this. I can make this even greater. Let's say it's 0.4. Let's see what happens there. Boom, a nice glancing collision. So we're good. So we built our collision model. Now, what if I want to do another ball? Okay, I want to have another ball collide. I'm going to leave it at that angle. So if I want another ball to collide, what I'm going to do is to get rid of this momentum thing. I don't really care about this anymore. I can get rid of that. But I am going to print b1.pos at the end of the collision. So let's do that. Right there. So that's where that ball ends up. What I want to do is to put another ball right there. So let's put the 2 ball. What color is a 2 ball in Python? I mean in Pool. I'm looking it up. It's blue. Yeah, it's blue. So I'm gonna make it cyan. So let's make another ball. I'm gonna put it at that location. So I'm actually gonna highlight this. But now I'm gonna need another. I'm gonna have to do a little bit more work here. So there's B1. Let's just go down here and say B2 equals sphere. Position equals vector that. It's exactly where it's at. Radius equals R. Color equals color dot cyan. Make trail equals true. B2.m equals ball m ball. B2.p equals B2.m times vector 0, 0, 0. Okay, now I'm going to need another force. I called that FC. I should have called it FC1. I'm going to change that. FC1, 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 1. Let's make sure it's still running because I changed a bunch of stuff. Okay, so there's my cyan ball, and it ran. Everything's great. The first thing we're going to do, if I want that collision, I'm going to need to run this for a longer time. So let's run this for 1.3 seconds. And I need another force. I don't need to put it up there. I can call it F12. And then I need another R12 equals B2.pos minus B1.pos. And then I need the same thing, but for the next one. If mag R12 is less than 2 times R, then there will be a collision between those 2 balls. And you'll notice here, I'm not checking for collisions between the pool on all the balls. I already know what's going to happen. I know that one ball is going to hit the 2 ball. I don't care about the cue ball anymore. So I'm not going to take that into account. If you want to make a real pool game, you'd have to check collisions between all of the objects, and this is not the best way to do it. You could do it this way. It's just probably not the best. So now I can say F12 equals negative K times 2 times R minus, I'm just doing the same thing, but now instead of RC1, I'm have R12, times norm R12. And then down here, F1C, ball, that one's fine. This one, ball 1, it's actually going to have 2, it could have 2 forces, one of them may be 0. So I'm going to say plus this, plus F12. And then I need to do this for B2.pos. Can you see that? Yeah, let's see. B2.p, sorry, equals B2.p minus F12 times GT. Now I need to update B2.pos. B2.pos equals B2.pos plus B2.p times GT divided by B2.m. Done. Okay, let's run it and see if it works. Okay, so it did, but that was a head-on collision. I don't want a head-on collision. I want that blue ball to actually move more horizontal. So let's shift it up a little bit. So here's my position. I want to shift it up. So it's negative 1.8. Let's say negative 1.2. And delete that other stuff. Okay, so you can keep doing this and doing collision after collision after collision. I can just print out the location of that final ball and then use that to find out where to put my next ball, and then shift it around and make another force, blah, blah, blah. If you have too many collisions, this is a mistake I made. You do not want, if you have too large of an impact at the beginning, you're going to lose a lot of the momentum in that and energy in that ball. So these are going to be going slower and slower and slower. It'll still work, but and you have to extend the time and so forth. But that's it. Pool ball collisions. Is the total momentum conserved? You can check. Is the kinetic energy conserved? You can check. That's your homework. So you got to actually do it. I'm not going to grade it, but you should do it. Code down below. If you want to play with this, you should. And there you go. Have fun. Don't hurt yourself. And break the code. That's the best way to learn. Good luck.